Hello dear students, in this lecture we will learn more details about the Chapman's theory. Okay, so Chapman's theory by definition is a simplified mathematical treatment which gives production rate with respect to height and solar zenith angle. So, the most important independent parameters are the solar zenith angle and the altitude, and production rate, which keeps changing with respect to these two parameters, will be derived. Okay. Now, so you can go back and refer to the basic atmosphere for which this mathematical treatment is valid, and most importantly, one of the most important assumptions is we are considering this for an oblique incidence. Fine. So, let us say we have the surface of the earth like this is the normal and this is the direction of the incident radiation. So, the radiation is coming at this angle. So, the angle is chi, which is the solar zenith angle. Yeah. So, the angle is defined as chi with respect to the normal. Okay. So, in the evening or in the early morning, sunrise and sunset, the angle is 90 degrees, and during the mid afternoon, the angle is 0 degrees. Okay. Right. So, we define the geometric height h in this direction, okay, which is, let us say, 0 kilometer means the surface of the earth and you are moving into the ionosphere. So, let us say 70 kilometers is the D layer. Right. Now, the direction in which the incident radiation is coming is this. So, we define this length coordinate as small s, okay, or we define it as ds. Okay. Now, as the beam is traveling in oblique direction, we can relate distance of dh and ds as dh is ds cos chi. Okay. ds is dh cos chi. So, ds is dh secant chi. So, the intensity I is traveling towards the surface in this way. So, the rate at which the intensity decreases with respect to the altitude as it travels along the path S. So, di over ds is of course proportional to the initial intensity I, and then the rate at which intensity decreases along the path S is also proportional to the number density, number of atoms or molecules per unit volume, di by ds. So, the atmosphere is horizontally stratified. So, there is no variation in density with respect to the height. So, as it decreases, it will depend on both these parameters, right. Since the intensity is decreasing with respect to the original intensity as well as with respect to the number density, we can combine these two expressions and write di by ds is equals to sigma n I. I have removed the proportionality and introduced a coefficient or a constant, which is sigma. I put a minus because it is a decrease. Okay. What is the meaning of this expression? This expression tells you that the rate at which intensity decreases with respect to the altitude is equals to absorption cross section times the number density times the intensity. Let us say we call these two equations as 1 and this as 2. Okay. Now, let us say we take C number of electrons. Okay. So, just a variable to use in our derivation, C number of electrons are produced for or by each unit of energy. each unit of. So, 1 unit of energy gets spent, so it will result in the formation of C number of electrons. Okay. So, if you define Q to be the production rate, Q is production rate. So, Q is the rate at which electrons are produced. Okay. So, Q can be written as, see, di by ds, rate of change of intensity with respect to oblique distance. Okay. Now, for this is the rate, for every unit of that change, C number of electrons are produced. So, di by ds, if it has to account for the total rate of change of intensity with respect to the distance, or total change in intensity which happened over a distance S, will result C times that many number of electrons, right? You understand? For each unit of this change, C number of electrons are produced. For the total change, total intensity change, since the beginning of the atmosphere till the complete absorption, if it is total, then the total number of electrons produced will be simply a multiple of C with the right hand side of that expression number 2, right. So, Q can be written as minus C times di over ds, which can be C sigma n I. Let us say we call it as equation number 2a. Okay. If you take dq over ds, what is this? Rate of production with respect to the altitude. You understand? So, rate of production is also changing. That is the basic purpose of the Chapman's theory. So, the rate at which electrons are produced is not constant throughout the ionosphere. It is changing at every altitude. So, the rate of change of q with respect to S can be written as dq by ds, right. Now, this production rate will reach a maximum. Q reaches a maximum, right. So, if you have to have the peak electron density at F2, you know it for a fact that Q is maximum at that point. It is increasing, it is varying, but it is reaching a maximum value. So, how do you define maximum in a mathematical way? So, if you take a derivative of Q with respect to S, dq by ds has to be 0 at that point, at the point of maximum. As simple as that, right. So, dq by ds has to be 0 at peak production height. We are doing the entire theory in terms of the oblique distance, not the vertical distance, right. So, dq by ds is equal to 0. If you substitute dq by ds is equal to 0, we can write, if the rate of production has to reach a maximum value, dq by ds has to be 0. Using the expression for this dq by ds, C sigma ni, okay, we can write as C is a constant, right. So, C and sigma, the absorption cross sections are constant. So, we can write, use the chain rule, I times dn by ds plus n times di by ds. These two are the only variables which are changing with respect to the distance, dn by ds and di by ds. We have already defined what these changes are, right. Now, we can divide this expression by C sigma n I. So, C sigma n I is Q, right. So, if I do that, I can get C sigma divided by C sigma n I times I dn by ds plus n di by ds. This should be 0, okay, or this goes inside. So, it will be 1 by n dn by ds plus 1 by I dn by ds, or if you still have this on the left hand side, which is nonetheless 0, you are just going to write 1 by q dq by ds, which is obviously equal to 0. Okay, fine, right. So now we have a relative derivative, right? We have change in n with respect to s normalized with respect to n itself. I should have written I here, di by ds. Change in intensity with respect to distance normalized with the distance itself, right? So is this expression valid everywhere? No, it's not valid everywhere. It is only valid at maximum value, because you have taken q to be varying and reaching a peak, right? So if at the peak, at this peak, if you want to find out, so the rate of change of dq by ds becomes simply 0, because it is reaching a maximum value and then changing to the other side. So this expression is valid, or we can write it as 1 by n dn by ds at the maximum value plus 1 by I di by ds at the maximum value to be equal to 0. This is the value at the peak. Okay. Now, from the earlier figure, we have written ds is equals to dh secant chi. So, ds is equals to dh secant chi. So, I can write s is equals to h secant chi. But these two distances are measured in the opposite direction. So, I can put a minus here, call this expression as, this is 2a, let us say this becomes 3 and this becomes equation number 4. S is equals to minus h secant chi. Right. Now, S and H are measured in the opposite direction, that is why we have a minus. So, we already know di by ds from equation number 1 as minus sigma ni. So, I can use this into using the above in equation number 3, 5, using 5 in 3. Okay. So, I can write 1 by n dn by ds at the maximum m plus 1 by I minus sigma ni is equals to 0. Okay. Let us say we call it as equation number 6. Okay. What have we done? Just look at this. So, the rate of change of intensity with respect to oblique distance is proportional to the intensity and is also proportional to the number density. Combining these two proportionalities and introducing a constant, we got minus di by ds as sigma ni, and if there is an incremental decrease in the intensity over the distance, and if it is producing c number of electrons, for the total change of intensity with respect to the distance, it should be a multiple of c. That is what we have done here, right. And now then we have introduced the rate of production as q, and the rate of production is also changing with respect to the altitude, not in a linear way, not in an exponential way, but in a way that it becomes maximum at certain point and then starts to decrease. So, in order to accommodate that possibility in terms of simple mathematics, we can write dq by ds is equals to 0 at the point where it is changing its slope, it is the direction of slope. So, then we did some simple algebra. We have a expression for the rate of change of intensity with respect to the distance, right, which is equals to minus sigma ni. Substituting that, we get this expression, right. Now, let us look at di over ds. Okay, di over ds is minus sigma ni. I can bring the intensity to the left hand side. We can write di by I is equals to minus sigma n ds, integrating on both sides between I to Im di over I is equals to minus sigma integration between infinity to s n ds. Okay, why did I choose the integration limits like this? See, I have this expression di by ds, which is telling how the intensity changes with respect to the oblique distance. So, intensity is somewhere at the beginning is I, okay, to begin with the initial intensity. By the time it travels an oblique distance of s, at this distance what exactly happens is, at this distance q is maximum, or to indicate this maximum production rate we write q is qm. Okay. When q is equals to qm, I say that the intensity has decreased to a value of Im. Okay. So, this becomes the limits of integration for the intensity, and if infinity is the largest unknown distance from which the radiation starts to attenuate, then the distance it has traveled to s. So, this distance, the lower limit of the distance becomes s. So, the initial distance is infinity to s. So, the travel is from infinity to s, while the intensity drops from I to Im. Okay. Fine. So, that is how we get the limits of integration. If we do the integration, then we can write ln of I by I infinity, or Im by I, it should be Im by I, okay, is equals to minus sigma times n ds. Okay. So, n is the number density and ds is the distance. We can call this product as equals to n ds as capital N at an angle chi. Okay. Let us call this expression as 7a. Fine. Then let us look at the other term in the expression, 1 by n dn by ds. Okay. Now, see, this is where it gets interesting. This expression tells the change in the number density with respect to the oblique distance, right. But what we know for sure is that we know how the number density changes with respect to altitude. N is equals to n naught exponential minus h by capital H. The number of atoms or molecules that you can find at any given altitude will be dependent on the bottommost or the base level, and an exponential factor which seems to be dependent on the height as well as the scale height, right. But most importantly, this expression is telling you how the number density changes with respect to the vertical distance, but not with respect to the oblique distance, right. So, the variation that you know very well seems to be dependent on the height in an exponential way, but we do not know when you change the angle. See, this small s is not equal to small h, right. We already know that. See, there is a factor, there is an additional factor secant chi, which is just a number, of course, but that is scaling number. So, what does it do? It scales h to s. So, depending on the angle, s and h will differ by different magnitudes. Okay. So, that is the basic idea. Let us say if you have this dn by dh, okay, dn by dh, if you have it, okay, then you would have simply done 1 by dh of n naught exponential minus h by h, and you should have simply written n naught will come just like that, e to the power of minus h by h and minus 1 by capital H. This is what you get, dn by dh. But you cannot do that, because you cannot substitute n is equals to n naught e to the power of minus h, because now the variation is not with respect to h, the variation is indeed with respect to small s. So, we have to make a change of variables, or we have to shift the variables by using appropriate expressions, only then this will be complete. So, dn by dh is equals to, what I will do is I will rewrite this expression in terms of small s and small h. Okay. This is 1 by n, which is dn by dh. This is what I need, of course. Then I will get an additional term, and dH by ds, with the assumption that even if I cancel dH and dH, my original expression is intact. 1 by n dn by ds is 1 by n dn by ds, right. So that's the purpose of doing this. So now we know an expression for h is equals to minus s cos chi, or dH by ds is equals to minus cos chi. Substituting this, I will get 1 by n dn by ds is equals to minus cos chi for this into 1 by n dn by dh. Okay, so which is 1 by n dn by ds is equals to minus cos chi into 1 by n naught e to the power of minus h by capital H into minus 1 by capital H, which is equals to 1 by n dn by ds is equals to minus cos chi times 1 by n, which is again n naught exponential minus h by h times n naught exponential minus h by h times minus 1 by scale height. So this will get entirely cancelled. We will get 1 by n dn by ds is equals to cos chi divided by capital H. We will need this, of course, and then we also need this to be substituted into this expression, right. Now let us just have a quick recap of what we have done in the name of mathematics for Chapman's theory. Our objective was simple. Our objective was just to derive an expression for the rate of production with respect to the altitude and the solar zenith angle chi. How do you define the solar zenith angle? You define the angle with respect to the normal, that is with respect to the sun at the mid afternoon position. Okay. Assuming at the sunset and at the sunrise the angle is 90 degrees, okay, and in the mid afternoon the angle is 0. We have taken the radiation to be incident at an oblique angle chi, which you call as the solar zenith angle, and the rate at which this intensity decays with respect to the oblique altitude seems to be dependent directly on the original intensity and the number density which it is interacting with. Breaking this proportionality, we introduce a constant, a coefficient sigma, which is the absorption cross section, and we define for every unit of this intensity change along S, C number of electrons are produced. So, total number of electrons produced would be C times that, which is called as the production rate. And since we know that in the ionosphere, this is actually an input that you are giving in tuning the mathematical treatment as per the original observation. The original observation says the production rate reaches a maximum and it is increasing before it reaches maximum and it is decreasing after it reaches maximum if you are talking from the above, right. Using this simple condition, we are now modifying the rate of production expression and saying that at the maximum value the production should be 0. So, using that we have arrived at expression number 3. Now, in expression number 3 we have two terms, dn by ds and di by ds. So, di by ds tells you how the intensity is changing with respect to the oblique incidence, and dn by ds tells you how the number density is changing with respect to the oblique distance. We are trying to get the meaning of these terms in terms of what we know already. We know that the intensity decreases exponentially with respect to the altitude, but we do not know how the intensity will decrease with respect to a vertical altitude. We have derived that with respect to S, things are slightly different. Okay. The only additional scaling factor is some term in the units of angle. So, angle will change it, right. Okay, so now we will continue this discussion in the next lecture.